So let me share the screen. Okay, I hope that you can see the slides. Maybe I should make them full mode. Yeah, so I hope that you can see them. And these slides can be found on the homepage of the course, where the address is given here. You can quite easily get to this page just typing my name, Robert Muszyński, and Wrocław University of Science. Then you will find my homepage. This is page in Polish, but among the courses you will find the link to the scientific and engineering programming course, and you will get to this page. Or maybe you already have been there, so it shouldn't be a problem. Actually, I have sent you some mails where this web page address was given. Concerning the instructors, there are two of us, as I said, Mariusz Janiak, and you already know that that's not me, and Robert Muszyński, and I will conduct the first part of the lecture. So we will meet more or less for a half of a semester, and then Mariusz Janiak will teach you the rest of the course. So there is my office room, and office hours will be given on my home pages. But since we are in this coronavirus situation, probably you won't visit me in this room. The only meetings we plan to have are every second week, the stationary laboratory meetings. And that's it. If you would like to have some consultation, then simply we can make an appointment via Zoom, or we will just discuss your problems using an email. If it is if it will be a simpler case. Okay, so there will be final examination, so you will have to write the final test for that lecture. It will be announced exactly on course homepage, so please refer to that place. We plan to do it stationary, but if the circumstances will change, maybe it won't be made in this way. And to get the credit, you have to pass the final exam concerning the lecture, and of course complete the laboratory classes according to this, what I already stated in general, and I will give you more details when we will meet at the laboratory. So this is the case. Okay, what will be contents of this lecture? This I will explain you soon. But let me first start with some explanation what this scientific and engineering programming is. What do we mean by this? Of course, in general, you can feel what the meaning of this title is, but I would like to be more specific to specify the needs which scientists and engineers have, and to specify what kind of tools actually they can use. Probably there are some tools which you already use, tools which are used by engineers and scientists, but I'm pretty sure that that's not all what can be used. So first of all, when we start with the defining of the scientific, this element of the title, so we will learn very fast that this is something related to science. When we would like to define what science is, then we can refer to some dictionaries, like for example, Merriam-Webster dictionary, and there we will find that science, this is a knowledge about or study of the natural world based on facts learned through experiments and observation. And when we ask what a scientist is, then we can simply say that probably some of you, if not now, in near future, hopefully you will become, some of you will become scientists, but in general, we can say that this is a person who is learned in science, who works with science. Now we can switch to the second word, engineering, and of course, this is a function of an engineer. This is what an engineer simply does. But also, referring to the Merriam-Webster dictionary once more, this is the application of science and mathematics by which the properties of matter and the sources of energy in nature are made useful to people. So engineering, this is just making a nature more useful for people, but this is made by application of science and mathematics. This is what this definition states. So to be an engineer, we have to know science, the results, the achievements of the science, and we have to know mathematics, which is a basic tool used to explain many things which concern the nature. So going further, we can ask who is an engineer. So of course, once again, some of you, let's hope at least, and we can refer for more concrete definitions to dictionaries. And what is maybe a little bit surprising, in Merriam-Webster dictionary, we will find only one part of this word, one part of definition of this word. This is simply a designer of engines. So this definition says the origin of the word. So everything started with engines, but we know that nowadays engineers don't work only on engines or with engines, but with many other things. And looking at different dictionary, Oxford Dictionary, you will find more general definition that this is a person who designs, builds, or maintains engines, machines, or structures. So extending these definitions apart from engines to machines and structures, it makes that the engineer can work almost on everything. And as you can see, this is a person who thinks how these structures should look like. The engineer is a person who try to build these structures, first in a kind of prototypes, then in final versions. And finally, what is maybe less interesting, this is a person who maintains, keep running these machines or these structures. So these are the tasks which engineer does. Okay, so we already know that scientific, this is related to science, engineering, this is related to design. So we have the last one word in our title, programming. So the simple definition is that this is something related to programs. Of course, when we say programs, we think about computer programs. And in general, programming, this is the act of creating computer programs. So this is what you already know, and probably we don't have to spend much more time on this part of the definition. So we will learn about this, how to use computer programs to fulfill the needs of engineers and scientists. So now it's time to ask what kind of needs do they have? What do they do in general in their work? So concerning scientists, they simply acquire knowledge, describe nature, and predict the behaviors. So they would need the tools which will help them to do this kind of work. Concerning engineers, they invent machines, design machines, analyze machines, build machines, test machines. So they do a lot of stuff with different kind of machines or structures, as it was said on the previous slide, and they also keep machines running. So unfortunately, the last task is not very challenging, but many of you probably will be devoted to it. A lot of engineers nowadays just working on keeping machines running. But of course, you can think also about these elements which are given on our list earlier. So that's quite important. And what is the manner in which the scientists and engineers work? We can observe a kind of a process which is formulated in a cycle. So in this cycle, usually there are three elements which are repeated. So we have something what can be called the pre-processing. So this is the stage on which the definition of the model and environmental factors appear. Then we have the analysis phase, during which the engineers and scientists try to understand the behavior, try to verify what they have stated. And finally, we have post-processing of results. So in general, one can say that this is any kind of visualization. So we make the thing real. Of course, not only preparing the machine, the engine, but also making all kind of other stuff like for example, preparing the documentation, which is usually a necessary element of each device. Okay, so what kind of tasks they perform in this cycle? These are in general three different tasks. This is just modeling, simulation, and visualization. This visualization is something really quite general. So this is not only visualizing things on a computer screen, of course. So you have to keep this in mind. And now we can specify what kind of tools these scientists and engineers use for the task. What kind of programming tools do we have to perform the task on this stage? Since we won't deal here with the whole process of this, what scientists and engineers do, only with the programming stage, we will now look at these tools. So of course, these are programming languages, and there are plenty of them, different kinds. You probably know already several languages, can program with them, and this is a thing which is quite obvious. Very often these programming languages are provided with some additional stuff, and we get some programming environments. What is quite important in such environments, that there are usually libraries which make programming easier. Of course, we could write every program from the sketch without use of any libraries, but usually it doesn't make sense. There are plenty different cases which are programmed already, and we can simply use this what other persons have prepared. So knowing the libraries today's, this is a must in programming. Probably nobody today's programs without libraries. Okay, concerning these libraries, we will have many different kinds of libraries. So of course, there are some general purpose libraries, but we have libraries for linear algebra, in which we are quite interested, since the kind of tasks we are going to do here. Then we have physics engines, which allow us to simulate the behavior of different mechanical systems, and not only mechanical. Then we have differential equations solvers, since plenty of models of phenomenon and mechanical objects which appear around us are given in a form of differential equations. these solvers help us to simulate the behavior of such systems. Then we have some libraries for motion planning and automatic control, optimization, curve fitting, signal processing, machine learning, and many, many more. But I think that these are the basic libraries which you probably would need to use. And to get an idea how many such, just a moment. Okay, and to get the idea how many of such systems do we have, just please go to this Wikipedia page to see the list of computer algebra systems which you can utilize at the moment. You will be surprised probably how many of them there are. Of course, apart from these programming environments with libraries, we have also simulation environments. So this is something more general, which provides us not only tools which make programming possible, but also all other elements connected with the simulating of the environments. And we will learn here mostly about this simulation environments. Of course, there are plenty more tools, all this case, CAD, FIA, FIM, etc. stuff, which we won't deal with, but which also make easier the engineer and scientist work to deal with other stuff than this basic, which is connected with work. You have somehow manage your work. You have to prepare the documents. You have to allow the communication between members of teams. So all these tools also today are prepared with use of computers. One can say that computers today are everywhere. Okay, so if you look at these tools, one can say then they should be effective, efficient, and impressive. And one can say that they should be effective like Mathematica or MATLAB. They should be fast like, for example, C, and impressing like, for example, GNUplot. So these are tools which appear different kind of properties, but they applied all together can make our work really quite easy. Okay, so here on this slide you have a list of some basic tools you will deal probably with. Some of them my colleague Mariusz Janiak will explain, will present to you. And among them, as you can see, we have some libraries, we have some algebra systems, then we have some physics engines, which allows for the simulation. We have some simulation environments and some more tools which also can be used. This is just to give you an expression that there are quite plenty useful tools available you can use during your work. And of course, we have these simulation environments, and among them, I think that most powerful are two of them, MATLAB and Mathematica. Probably you already have dealt a little bit with MATLAB because this is more popular tool, and you will learn more during the second half of the semester about MATLAB. But usually it is the case that nothing you know not very you don't know much about Mathematica. Maybe you have found useful for you the Wolfram Alpha page, because nowadays in secondary schools a lot of pupils use this page to do mathematics exercises. But Mathematica as a system alone is not very well known. So we will try to learn about this Mathematica, first of all language, but also the whole environment. So I hope that you will see how to use it. Maybe this is a good moment, or maybe I will finish this slide and then we switch to this Wolfram Alpha page to shortly describe how it is related to Mathematica and what is the idea of the system, because it is not only useful for making math. Okay, the idea of preparing the Wolfram Alpha page is a little bit different. But to don't change the sharing of a screen too often, simply let me finish these slides. There are not many of them, and then we will switch to this Wolfram Alpha page. So in general Mathematica, this is a mathematical symbolic computation program, sometimes termed also as a computer algebra system, which provide us which provides us a lot of technologies. So first of all, we have the Wolfram language. This is quite important, that Mathematica is based on a programming language which is called Wolfram. Then we have a kind of interface, which is a notebook interface, also very well structured, an interface which can be programmed. So this is quite important. You will learn quite soon what is the basic idea of making Mathematica programs, and you will find that this is really something very uniform. So we have also here provided the algorithm base and knowledge base we can use. So we don't have to write everything from the sketch. We have Wolfram engine and also Wolfram cloud in which we can work. What kind of knowledge does it cover? So there is really plenty different areas. In general, when you work with Mathematica, you shouldn't ask questions, is it possible to do something in Mathematica? But you already should start with the question, how to make this in Mathematica? Because almost everything in Mathematica can be done. I will try to show you, you have already probably looked through these demo projects which are on the demonstration page of Mathematica. So you already have an impression probably that this is quite powerful tool. It is used not only by scientists and not only by engineers, but also, for example, by artists. You can create, compose music, you can make paintings, or I really don't know what else using the Mathematica. In the net, you can find galleries which show paintings prepared with the Mathematica, for example. Okay, but this is not what we will work with. So first of all, looking at the area you can be interested in, we have the symbolic language, so something with which you probably haven't dealt earlier. I will try to explain you what is the difference between numerical and some symbolic language. Of course, you have some numerics, some math computation, algebraic manipulation, differential equations, control systems, robotics. This is the area in which I'm working in. So we will do some robotics during these exercises. Then we have data analysis, signal processing, computer vision, visualization. But if you are interested in chemistry, for example, you have whole bunch of modules which are useful to deal with chemistry. If you are interested in optics, in physics, any kind, you can work with this in Mathematica as well. Mathematica started as a system which was designed for mathematicians, but very fast it changed to very universal system which can be used by many different engineers and scientists in really a lot of different areas. If you would like to know what are the Mathematica features, I provided them here on one slide. These are the most general. Of course, we won't analyze them here. This is just to give you an impression that there are plenty of different features. You can, by yourself, look through this list and try to get the impression, more closer impression about this. But we will go through this just learning Mathematica. How to start to work with Mathematica? Unfortunately, there is no free access to Mathematica license, even for students. You can get Mathematica license for students, but you have to pay for it. It is not, maybe it is not very expensive, but still you have to pay. We are providing the Mathematica license for you on our camp. So in our laboratories, you will be able to use Mathematica system. And this is why this part of laboratories we will make stationary, since there is no remote access to Mathematica. You can use the CDF player to view documents, and you can use the Wolfram Alpha, but also the Wolfram Cloud. I really quite surprised why it is not put on this slide. I was pretty sure that I have added this. Okay, so maybe it is only on the web page. So just remember, I will make sure that this Wolfram Cloud is placed on this slide, but you already know about this place. So these are the elements, these are the places where you can work with Mathematica. And let me switch the window now. So we will try to go to this Wolfram Alpha page, because you already have been in Wolfram Cloud. Just a moment, please. Okay, I hope that you can see now the web page of mine. So as I said, this is only in Polish, but from this web page you can get to scientific and engineering programming, and here you have this page we will use here. And what I would like to do is to go to Wolfram Alpha page. So it is said that Wolfram Alpha, this is computational knowledge base. Pro student, I don't need this. Mon Dieu. Okay. So the basic idea of this page is to be internet knowledge provider. So Wolfram Alpha can look for you for the knowledge in the web page, in the web, as the Google does. So simply you can try to find something using this Wolfram Alpha interface. But the difference between Wolfram Alpha interface and Google interface is that Google interface provides you the information found in web in the form as it is there. Maybe with some additional structure, but in general, it cannot utilize this knowledge to make some computation. Wolfram Alpha is supposed to make the computation to manipulate with this knowledge for you. So you can acquire some knowledge, then perform some computation on this and obtain the result the results of this what you have ordered to do by Wolfram Alpha. So this is the main difference. Of course, you can look through these basic elements here, but let me illustrate what I mean by this computation, what can be done. Of course, it can be something simple like adding 2 to 2. When you press enter button, then you will learn that 2 plus 2 this is 4, but you will have also some visualization. You will get English word. You will have illustrated this in some different form, and also you can learn, for example, that typical human computation time differs on age, and for example child on age 6 will compute this within 3.2 seconds, and somebody like you will compute this in less than 1 second. So maybe this is not very useful in this situation to know this, but since there is nothing more to be provided, Mathematica, Wolfram Alpha gives you such information. But of course, you can try to do something more complicated. For example, you can compute integral, let's say, of x. As you can see, there are plenty of possibilities, but let's take something quite simple, integral of x squared. So you will learn what it is. Apart from this, you will obtain the plot of this integral, and you will learn about some related queries which are here. So of course, if you want to solve any equation, you simply write solve. Let's take the first equation there is, and you will obtain the solution of this equation. Apart from this, you will obtain the position of roots in complex plane and sum of roots, product of roots. So this is what you can get. So this mathematics stuff you can do with Wolfram Alpha, but as I said, you can make much more. And let me do some simple stuff. For example, let's say that I would like add 1 apple. Oh, Mathematica already says that Wolfram Alpha already says that 1 apple goes well with 2 oranges, but apart from 2 oranges, but instead of 2 oranges, let add 2 carrots. What we will learn? Mathematica first acquire knowledge about what apple is, what carrot is, and then try to serve us some information about such combination. So it is assumed that we have 1 standard apple, and serving size of this apple is such like specified in this table. We have 2 carrots. Also here you have typical weight of a carrot, average weight, let's say. And then for such apple and such carrots, you know that altogether these are 118 calories. There are some fat calories in them. You can learn what is the daily value of fat, cholesterol, sodium, and so on. So this is perfect place to analyze your diet. If you have eaten something or you are preparing some meal, then you can simply compute everything what is connected with this. As you can see, there is quite a lot of information about these elements. So this is one of the kind of application of Wolfram Alpha. Several years ago, accidentally, when I was typing this example for students, instead of writing carrots, I have typed parrots. And the question is, what you will get when you add to one apple two parrots? Mathematica acquires some knowledge. I already know this because I have computed this for several times since then. And you can see that now apple, this is just not a kind of fruit, but this is a computer company, because there is also a company called Parrot, and Mathematica now assumes, in the context which you have provided, that you would like to know about one share of Apple company and two shares of Parrot companies. So at the moment, you having one share of Apple and two shares of Parrot, you would have something like 470 zlotys. I have such a localization, so it is given in zlotys. And here you can see what was the history of change of these elements. Here you can, for example, see what are the companies' logos, also some Wikipedia summary about these firms. So you can see that this what is provided by Wolfram Alpha. This is something similar to the stuff which would be provided by Google, but the difference is that here you have this computation part. Mathematica already has post-processed this information for you and provided it in the form you would like. For example, let's see to some other, you can see that, for example, you can check what is the weather somewhere, but let's refer to our city we are in, to Wrocław. And let's see what Mathematica will give us about this city. So we will get the information where it is placed, what is the population, where it is placed on a map of Poland. We have got a local map, current time, current weather, nearby cities, also nearby airports, what else, geographic properties, and so on and so forth. So you can learn quite a lot of stuff about this, and you can manipulate cities as well. For example, let's add to Wrocław, Warszawę. I would try to write it in Polish. I wonder if it will work. Yes, it works. So it has been translated automatically. And in the sense of adding these two cities, Wolfram Alpha provides us only the total population of these two cities all together, because somehow it is assumed that it only makes sense to add the population. Maybe you could also sum up area, but for some reason it wasn't sum up here. So here you can do a lot of such stuff, and we won't work with this anymore, because also this kind of stuff can be done in Mathematica. So I will show you how it can be done in Mathematica, and then you simply be able to apply, of course, in limited version, this in Wolfram Alpha. Okay, so let me stop sharing this screen. And now we will switch to the next slides. Just a moment, please. Okay. So we will switch to slides concerning Mathematica. because from now on we will work with Mathematica. And since Mathematica, it is such a universal tool, so why shouldn't I prepare slides for this part just in Mathematica? So I hope that you can see the lecture 1 Mathematica Basics, which are the slides prepared in Mathematica. So we are already in Mathematica environment. Okay, so let's start this part. So how to start and quit, this is quite important to know how to start the system and how to finish the work. So first of all, you have to know that there are two front ends, user front ends in Mathematica. You have this graphical one, which I'm actually using. So you simply run this by a proper command in command line, or just by pressing the icon on your desktop or somewhere. And you have also the terminal front end, which is much simpler, but which allows you for batch computing. So you can prepare scripts for Mathematica and just compute them automatically in batch mode. And then to run this terminal front end, you have to type math command in a command line. Okay, so when you want to input expressions, we will generally talk here about this graphical interface, because most often you will work with this interface. At least you will start working with this interface. So if you would like to input some expressions and make computation on them, you simply in this notebook have to type in an expression and then use the enter key to compute when you are in the terminal mode, or use the shift plus enter keys to compute. So this is the first thing you must know, that to compute stuff in Mathematica front end, this graphical front end, you have to use not only enter but pressed with shift key. To terminate Mathematica, you use in terminal mode the quit function. In fact, every command you provide in Mathematica, this is just a function which do some mathematical computation or just do some functions you require. And in graphical interface, the easiest way is to use menu or keyboard shortcut for these menus. When you need help about the elements, simply type the name of this element with single or even double question mark in front of it. So for example, when you type question mark sign, then you will get simple definition of sign function, and also here you have some reference to get to the help page concerning the sign. Unfortunately, in my case, it has opened in other window, which probably you can't see. So maybe for the time being, I stop sharing this window and start sharing the whole desktop. Okay, so I hope that you can see now my desktop. So when you click on these arrows, then you will get another window, which is window with help concerning sign function. So you can go to the details, but this is usually not necessary for you. But you have basic examples and basic description of this function, but you have much more: scope, generalization, applications, properties, possible issues, and net examples. So usually there are plenty of knowledge in these elements. So you can see there are some simulations, some playing some tones. I don't know if you can hear this, but I hope that yes. And so some other stuff you can use here. What is more important is that these examples which are provided here are computable. You can put the focus on them, and when pressing Shift with Enter, you will compute them. So for example, when you change something in this element, then you will obtain different result. So you can experiment with this. So this is really something very important and something useful for you, since not only you are provided the knowledge, but also the place for experimentation. Okay, so just please keep this in mind, because you can learn quite a lot of from here. Of course, you can open this help system just coming from help menu, where you have Wolfram documentation, and here is plenty of knowledge covering all the stuff you need to know. You can search this, of course, but you can go through some elements which are divided in some sections here. You have also introduction to programmers, you have some books and so on and so on. So there is plenty of knowledge concerning the application of Mathematica. And this help is a place which is worth looking at, because a lot of stuff is really quite useful. Okay, so what I would like to say today on this stage is to ask you to don't run multiple Mathematica instances in our laboratories if it is not necessary. And usually for you, it is not necessary, since it is enough for you to run a single Mathematica. Every instance of Mathematica takes one license site, and we have only 40 licenses of Mathematica, maybe 41, I can't remember exactly, licenses of Mathematica. And if you open several Mathematica windows in several instances, then you take quite a lot of instances. Now, when there will be just a few of you in the laboratory, maybe it won't be a great problem. But for example, when there were 15 person working in the laboratory at the same time, and some of you has opened 3 or 4 instances of Mathematica, then the other couldn't open any of them. And we have lack of licenses. So the problem is that every time when you double click the Mathematica file icon, or open a file directly from the web page, for example, or by clicking the icon of this file, it brings typically a new Mathematica interface, which is a new instance. So you can use these new instances not knowing about this. So every time when you want to open a new file, simply use the file and open menu, file open, then you will obtain another window with Mathematica, but this window is running on the same Mathematica kernel. So this is quite important to do this, because otherwise we can get into troubles. Okay. Let's look through this, what we can do in Mathematica. Let's see what are the basic computation. You have already seen some of them on Mathematica Cloud, on Wolfram Cloud, on Wolfram Alpha, but I will try to show you, to explain some details which are not met in other programming languages. So we would try to make a little bit familiar with Wolfram language by this. So first of all, you can make some numerical calculations, and among them some arithmetics. So as you could see, you can add 2 plus 2, or you can add this in different versions. As you can see, the results are different, because there is a result where we have only a digit, a single digit 4, and also there are results where apart from this digit we have also a period after this. in general, the period means that this is approximate result. Mathematica can make for you exact computation. Maybe I will open a new notebook to show you this. For example, if I divide 1 by 3, then I will obtain 1/3. But if any of these numbers is approximate, then I obtain 0.333. So this is approximate result, as you know, and this is the exact result. Mathematica can be as exact as it is possible, and all the time when you don't ask it to provide approximate result and it is possible to provide exact result, Mathematica will does it. When you would like to change this exact value to approximate one, you use function which is called n. In general, Mathematica uses functions in such a way that you provide the arguments for this function in square brackets. So this is the first type of brackets we have in Mathematica. In general also, instead of such notion, you can call the function after the argument if there is a single argument. Then you use such double slash notion, which is a kind of post notion, where when the name of the function is placed at the end. So this is what it is possible to do. And for example, we can compute the power of 2, let's say the 100 power. So we will see what is the exact number, but also you can get the approximate result. Just please remember, if any component of the expression is approximate, then the whole expression is approximate. If all the components of the expression are exact, then the result is exact. And Mathematica can compute really huge numbers, because you can compute the 100th power of 2, but if you would like to compute the million power of 2, you will get the result immediately, but you can see that this is quite long, and it is hard to say how large it is in fact is, because we have plenty of digits in this result, but it was computed at once. So this is the next property of Mathematica. There are no limits on variables. Variable can be as large as it is necessary. So we don't talk about range of the variable. The variables, one can say, are unlimited. Of course, if I would like to get the approximate result, it is enough to make, for example, these two to be approximate. Then I will see that this number have 301,029 digits, since it is multiplied by this multiplier. And the other way to get this result approximate is just to apply the n function, numeric. So you will obtain exactly the same results. So you can see now that the computation possibilities of Mathematica are really huge. Here we have some more examples. For example, when we add some rational numbers which are exact, we obtain the exact result, but adding to it anything what is approximate, we will get the approximate result. Of course, any element of the computation, when it is approximate, the result will be also approximate. And here is another feature of Mathematica. You can use this percent sign to refer to previous result. So this means take the previous result and add to it this number. Of course, instead of 1%, you can specify 2%, 3%, and so on and so forth. And it will mean not last but one, and the third from the end, and so on and so forth. So when you use Mathematica as a sheet of paper, it is quite useful to work with Mathematica in such a manner. You have defined some mathematical constants in Mathematica. For example, there is constant pi, and if you ask Mathematica how much is it pi, it will answer that this is pi. It cannot be provided in any other way because this is exact number which you cannot express in any rational form. But if you would like to know what is an approximate value of this pi, you will learn about this. You can have as many digits of pi as you wish. For example, here is the 300, the first 300 digits of pi, but if you would like to see, sorry, if you would like to see 40 hundreds of first digits, you will have them immediately. So you can see that Mathematica computes it in almost no time. This is really powerful tool to make computation. Okay, so the basic manipulation, you can just make some basic algebraic expressions. You can have exact numbers and approximate numbers. This is what goes from this slide. The next thing is what I have already mentioned, is that when you are applying, when you are using Mathematica function, you have to use brackets, square brackets, to provide the arguments for it. And there is a rule that all built-in functions in Mathematica starts with a capital letter. So it is quite good. It is quite good to define your functions with names which will start with small case letters. Then it is quite easy to distinguish between what is built in into Mathematica and what is your own. But of course, you don't have to follow this rule. Okay, so once more, let's see. When I would like to compute sine of 1, Mathematica return me sine of 1, because this is exact number and you cannot provide in any other form exact value of sine of 1. Of course, when it will be something what is approximate, then you will learn that this is such a value. For some exact values like sine of pi or sine of pi over 3, you can have exact values, and you could see that if it will be 0 or square root of 3 over 2 for this pi over 3. So there are cases when the exact numbers can be provided. And for example, sine of pi over 5 also can be computed as an exact number, and sine of pi over 13 cannot be computed. Mathematica follows one general rule. If you cannot compute something, just don't do it. So usually you will have the result returned in a form as they were input in Mathematica when there is no possibility to compute them. You can specify the arguments of trigonometric function also using the degree symbol. You can have here also some more functions. And for example, when you compute tangent of pi over 2, you know that this is infinite number, you will get complex infinity. Mathematica have something like infinity and can manipulate with it. Okay, also when you use other functions like square root of 16, this is 4, and square root of 2, this is square root of 2. You can have numerical value, approximate value of it. And also when you take a square root from the negative number, you will obtain the imaginary part of this element. So this is just the basic sketch about the functions in Mathematica. So you know just to use the brackets always when the function has when a function has arguments, doesn't matter one or more, then specify them in square brackets. Here you have summarized some basic functions which at the beginning can be useful for you. Okay, what else? What are the computational techniques? I already have mentioned a little bit about this recalling the results, so you can recall them using this percent sign. Of course, you can see that every input has a number, and according output has the same number. Then you can refer to these results specifying this number. So if I compute and there is the output number 7 or output number 5, then writing %5 will recall me these results. So this is what is summarized here, but this is not very convenient for programming. In general, I recommend you to use variables. So this is what we rather will apply. Of course, when you work with Mathematica as a sheet of paper, this is what I haven't mentioned yet, but this notebook, what we have here, can be just used for making some simple computation, which is just computation auxiliary to our work we are performing. But also in this notebook, you can have some programs. You can program in Mathematica. So these are two basic uses, use cases of Mathematica. So when you are using it as a sheet of paper to make the side computation, then this percent can be used. But please don't use them in your programs because it can be really misleading. So let's switch to variables. If you would like to set a variable, you have to use one of these operators, equal sign or equal sign in front of which we have column. And on this stage, for you, one could say that there is no difference between these two operators. In general, it is so that the first one sets immediately the value and the second one sets delayed value. What is the difference? The difference is at the moment of computing the expression. So this expression with this operator is computed at the moment of the definition, and this value of this expression is computed at the moment of its usage. We will deal with this case when we will get to more complex situations. You will see how it looks like. So, for example, you can define these values. When you have defined them, then you can manipulate them. Also, in other notebook, if you ask what is y, this is the notebook running the same kernel, you will see that this is 5. And you can add to this y 4, then you will obtain 9. So this is just a variable which has a value. And what is quite important in Mathematica is that variables can have no values there. For example, if I say clear y and ask what is the value of variable y, Mathematica say that y, this is just a symbol y. In numerical languages, you cannot have the situation where the variable has no value. Maybe this variable is not initialized, then the variable has unknown value. You don't know what is the value of variable, but the variable always has a value. Here, you can have the situation when the variable has no value. So this is quite important to remember, because the consequences of this case can be quite different. Okay, when you are typing expressions, you can type at the end of them semicolon, and semicolon simply means don't display results. So you can see that when I compute this stuff, then nothing appeared, like here, when I have computed this stuff, then I have obtained these 3 results. But of course, all the definitions were performed. When I ask what is X, what is Y, I will be learned that here it is 5 and 5 because of these definitions. When I run this part, I ask what is X and Y, I will learn that this is 9 and 9. So you can mix this stuff. Of course, you can put also several expressions in one line, and then this semicolon will say where is the beginning, where is the end of the previous expression, and where is the beginning of the next one. So this is what you can do here. Okay, so this equal sign, this is function set, this colon equal, this is set delayed, and setting dot, this is function clear variable. Okay, in fact, everything in Mathematica is a function. Even this notebook I'm showing you, this is a function which is called notebook. Such a cell which we are working with, this is a function with the name of cell. So this is quite important that in Mathematica everything is treated uniformly. So this we will talk about this later on also, but from the beginning maybe you should remember these facts. Okay, so let's try to make something more complex, and let's switch to lists of elements. If you would like to have several elements you will work with, for example, to perform the same operation on all of these elements, or to treat these elements as some more complex objects. Look at this. These three elements looks like a vector, three elements vector. Then you have to use braces or curly brackets, one can call them also in this way. So just please remember about this. This is the second kind of brackets in Mathematica, curly brackets, braces, which you will use to make lists of objects. And here you have some examples. For example, you can have an object with three elements, then you will get it. And you can, for example, square all these elements and add to all of them 1. So you will obtain these results. Or you can subtract two elements, but as you can see from these examples, they have to be of equal length. So we have three element list and another three element list. We can subtract one from the other, and we will get the result. If there is 4 element list and 3 element list, we cannot do this. Mathematica simply will tell us that objects are of unequal length and they cannot be combined, and simply will return the result with no change, one can say. Of course, there is such a change that this minus was put in front of all the elements. This is what Mathematica could do, and then these two objects are added to each other instead of subtracted. Okay, you can have the exponent, for example, or sine function, doesn't matter, with the argument being in a form of list. So, for example, when we have some elements, then we will obtain the the list of results according to this what has been done. Okay, so the list was 2.5, 4, and 5.5, and we have obtained, since two of the elements were approximate, we have obtained two approximate results, and the last one and the middle one was exact number, so we have obtained exact value. But of course, we can get the approximate value by applying of this function n I was talking about already. You can substitute such a list to a variable, and then you can operate on this like it was done here. So this is what you can do with your elements. And we will think about such a list as about a vector. For us, this will be interpreted as a vector. So when we will operate, for example, in three-dimensional space to describe the position of an object with x, y, z coordinates in Euclidean space, then we simply will use such a list of three numbers which will specify x, y, and z position of the elements. So please remember, this is quite important. When you have lists, like vectors, you can operate on them, taking a part of them. To do this, you should use these double brackets. So single brackets were used to specify arguments of function. Double brackets are used to specify the element, to specify the index of the element actually. And numbering of elements in Mathematica starts with 1. This is object number 1, 2, 3, 4. Actually, you can have also 0 here, but I will explain this later on. Just remember, this is not like in C language, where you number objects starting with 0. Here you number them starting with 1. So if you, for example, have a list of 4 elements, then you simply can take the second of it. Or you can take several elements from this. Let's say that we would like to take third, first, third, second, and fourth. Specify this as a list, since you can put a list here and you will obtain the sequence of the elements of this list as it was specified. Of course, when you have substituted a list to a variable, then you can take an element of this variable. So v of 2, this will be the second element from this vector which we have here. Also, you can set the value of a specific element in a list. Let's say that you would like to set the second element of v to 1. And then you will see that here, instead of 4, we have 1 on the list. This is how it works in general. Okay, so we are actually at the place where we can summarize this bracketology, what I have called here, in Mathematica. So you could see already that we have 3 kinds of brackets in Mathematica, but there is the fourth one, just parentheses, and they are used for grouping, and there is nothing more. So to work with Mathematica very fluently, you have to remember, if I would like to specify arguments of a function, I use brackets. If I would like to make a list, like a vector, I use braces. If I would like to index elements of a list, I use double brackets. And finally, if I would like to group some computation, I use parentheses. And you can use this parenthesis for such simple situation like changing the order of computation. For example, when I have 2 plus 4 times 5, I will get 22. Of course, I can put parentheses here and we will get 30 because first it will be the addition, but also you can group set of functions. If you would like to perform functions in a specific order, you can specify this order by using these parentheses. We will talk about this later on when we will try to put several functions together and make things more complex or solve more complex things. So I didn't mean that we would complicate something. Okay. Here is a good place, I think, to say you that, in fact, there are 4 types of function notions. You have seen already 2 of them, this postfix notion and this standard notion. So first of all, you use these brackets to have this standard notion. But when you have a single argument function, then you can apply this prefix notion, just typing the at sign between a function name and the argument. It means apply f at x. Or you can have this postfix notion when you use double slash to say that this has to be applied, the function f has to be applied to x. So this is quite useful because, for example, when I have some computation and I would like to apply sine function to it, so I can specify sine at the end. Oh, I have seen that this is exact number, so I can apply the next function. Let's say that this is that I want to have numeric function of this. When I would like to compute the exponent of this, then I can apply the next function. And you see, these functions here are specified in the order of application. If I would like to specify in a standard way, I have to put them opposite. So I have to put them in the opposite order. Okay, there is something wrong with this expression. Number I have seen. I have put double brackets here. So maybe this is good situation. I don't know if it is large enough for you. Maybe I should magnify this a little bit. So during typing time of the expression, if there is something wrong with the expression, then the part which is placed not in proper manner is displayed in red. And also you have here such a plus sign, which can be pressed and give you the communicate about the error. There is no closing bracket here, but in fact I have put too many brackets after n. And now this thing can be computed. Also, one additional thing, when there is something which is not defined in Mathematica, like for example, this FASAS name, it is plotted in blue. When I compute it, this is just FASAS. But for example, if I substitute to this FASAS, let's say this is a name of variable, any value, 5 plus 6, observe that its color has changed to black. So everything what is in Mathematica defined is print in black. If something is not defined, it is print in blue. So this is quite useful. For example, if you misspell any function or any variable name, then you will see this, that this is printed in blue. When, for example, you would like to type a function sine, when you start typing it, it is in blue, but after putting n, it turns to black. But if you put something else there, it is again typed in blue, since sine f is not defined here. You already have seen that when I'm typing, Mathematica try to make the completion to this, what I have here. So very often it is enough to choose something from the list, but also when you are typing, just press enter and then it will be fulfilled to this which is first on the list. So it makes much faster working with this. Of course, with each function, you have this information part where you can go to this help page and see what this function exactly does. So this is the way you can learn about functions. Usually, basic examples are enough to get the first feeling what this function gives you. Okay. And also you have this infix notion where when the function has two arguments, you can put the name of the function in between. This is, for example, sometimes this is useful, for example, when you try to join two lists, when you have one list in the front, one list in the end, and in between you have a join operator which joins this list. You can see how it exactly works. Okay, what I have mentioned already, and here is summarized. If you put several expressions in one line, then you simply specify the boundaries of the expressions by semicolons. Yes. Okay, I thought that somebody was talking something. Okay, and when you don't put a semicolon at the end of the expression, then Mathematica will compute these expressions, all of them, and return the result of the last. But when you put a semicolon at the end as well, then you obtain no results. So this is the difference. Usually, when you don't need the result, simply type this semicolon at the end, because it can be so that the computation process doesn't take a lot of time, but passing the result from the kernel to the notebook, it is quite time consuming. Especially in numerical computation, it can be so that Mathematica computes the result within 3 seconds and then transfer these results, which is huge, to the form which is readable for a human, and it takes 30 seconds. And altogether, you have to wait quite long, and this is not really necessary. So this is quite a good point to say that Mathematica has a kernel. I already have mentioned this, and all the computation is performed by this kernel. And you can access to this kernel via these front ends, the graphical front end or terminal front end, what I have already shown. So there is no other way to communicate with the kernel. Typically, when you run the notebook, the front end, then the kernel is run automatically for this. You can have several notebooks for one kernel, or you can have notebooks with different kernels. Here in evaluation part, you have tools for working with kernels. You can start, stop them, but we will work with a single kernel here. That's enough for us. Okay, so summarizing this, what I have said about functions, the most functions, built-in functions, are listable. It means when you provide the argument as a list, you will obtain a list of elements. You can take a part of list and compute, and you can compute and take a part. So these are two different cases. You see here from this list, I take the second element and provide it as an argument of sign. Here, I compute sign of all three elements and then provide the second element. Of course, the result will be the same, but it will take longer because you have to compute sign of many things instead of one. So just remember this. And here these examples of the notion. The n function can have single argument, as you could see, when there is arbitrary precision specified, but also it can have several two arguments, so you can use any of these notions which were applied here. And once again, I have a line with three expressions separated with semicolons. With no semicolon at the end, I've got the result. With semicolon at the end, there is no result. Another case, for example, I can have the expression don't display the result. Then I will ask what is A, what is B. Mathematica will answer me. Okay, so here is the case when I'm using in not very typical way the parentheses to change the order, because I would like to set 7 to B and then use this value. The set function returns the value which is set to a variable. So simply the 7 will be added to this form. Of course, I don't recommend you to do this in such a strange thing. For example, here is something even stranger, to show what is possible. So I want to set B and C up, B to be 1 and C to be 2. This expression returns value 2. Here D I set to 3. This expression returns value 3, and this 2 is added to this 3 and is substituted to A. I don't know what for, but you can do such strange things in Mathematica. Just be afraid of them. Because if you would like to do this in separate lines simply. There are some cases when you can do something like this, but I will show you them. So just remember, don't complicate too much, and remember that there is the Occam's razor law, which says that entities shouldn't be more complicated than it is necessary. So please remember and don't complicate stuff. Unfortunately, Mathematica allows you to complicate stuff really much. So you can make quite fast your programs to be not readable. But please don't do it. Okay, so now we will switch to, or maybe before we switch to this algebraic computation, there is one remark I would like to say. Simply, we have said that when we have a list of 3 elements, oh, sorry, there were values substituted. Okay, so maybe I will start a new kernel to don't have the values. Okay, so I have said that when we have 3 elements, we can treat them as a vector. So if we would like to, we can substitute to these 2 variable. Let's say that this variable will be vec. But when I construct something more complicated, I mean, I will put a list of lists. Let's say it will be 3 by 3. Lists. Then this element can be treated as a matrix. This is the first row of the matrix, this is the second row of the matrix, and this is the third row of the matrix. Mathematica even have such a function, sorry, not here. Mathematica has even such a function like matrix form, which allows you to look at the elements in this matrix form. So if I will ask what is a matrix form of vector, I will see that this is the vector. When I will ask what is a matrix form of my matrix, you will see that this is 3 by 3 matrix. And what I can do, for example, I can multiply them, but to make the matrix multiplication, you have to use the dot operator in Mathematica. So multiplying matrix by vector vec will get us this vector. I can display this in matrix form. So we will see that we have a vector with 3 components, which results from the multiplication of these elements. So in general, when you multiply in standard way, like 4 times 5, you can put this star, or A times B again, but also you can leave a space. When I type 4 space 5, this is a multiplication. You can even see that Mathematica in gray has put a multiplication sign there to let me know that it will be multiplied. And also A and B, when I put these two elements, I also will obtain the product of these two elements. So just remember this. Ordinary multiplication with star or with a space. If you would like to multiply matrices and vectors in a way it is done in Mathematica, in traditional Mathematica, you have to use this dot operator. Unfortunately, when you specify matrix times vector like this, or I think that even with a star operator, you will obtain the result since this is multiplied element by element. So you can see that the first element of matrix was multiplied by the first element of vector, second element of matrix multiplied by the second element of vector, and the same for the third elements. But this is not what we think about like a matrix multiplication in the traditional meaning of these words. Remember, when you would like to multiply this, use this dot operator. So this is small introduction to matrices and vectors you should know. And now shortly about symbols. This is something new in this system comparing to the numerical languages, to the numerical systems, because here we can make, apart from numerical calculation, also symbolic computations. So I can add numbers to each other, but also I can add symbols, or I can combine symbols one each other, and then I will obtain the results. So I can see that numbers were subtracted and the symbols also were subtracted here. Okay, so now I can clear the X and Y for any case. If there was a value, you remember that objects with no value are printed in blue, and for example, can have some algebraic expressions, some polynomials, for example. Or I can try to make some operation on these polynomials. I can expand them, I can factor them, I can compute even something more complicated. And you can see that here in these expressions, there are unknown variables. I mean the variables with no name. And as you can see, for example, this expression was somehow transformed. This expression was somehow simplified, and there are expressions which were left with no change. Why? Because when Mathematica doesn't know how to change the expression, it doesn't change it. So basic Mathematica principle is that it takes an expression and apply transformation rules it knows until the expression stops changing. So if I have no rule, the expression stops changing at the first step, so I return it as it is. If I know some rule, I apply them, and after recurrent application of these rules, when the expression stops changing, I return the results. So this is what you should remember. And look at this, that such expressions with symbolic elements can be regarded as a equation. And for example, I can substitute it to a variable. Let's say that I have the variable eqn, which is equal to this. And for example, I can apply function solve to this equation. To solve it, you have to know this. If you don't know, simply refer to manual to help. The simplest case is that you can see that there are two cases where you have the equation and the variable. Let's try to solve it with respect with x. Mathematica will complain that it cannot solve this because this what I have provided is an equation. Why it isn't equation? Because there is no equal sign, okay? So I would say that it has to be equal to 0, and now Mathematica has solved it, providing me the results. So you can see that here I have used the double equal sign, because when you type, wait a moment, for, let's say, 4 equal 5, you will obtain the logical expression. I'm asking here if these two elements are equal. It can be true, it can be false. So I would like to know what x should be to make this equality true. So Mathematica tried to solve it with respect to x. And as all elements of this polynomial were exact, you can see that my result is also exact. So I have, for example, a square root of 177 here placed like it is. Okay, so this is what you should know, and maybe this stuff I will explain you next time, because anyhow we won't be able to do everything today. We are almost finished. Wait a moment. Okay, we will finish this next time. As you can see, the vectors and matrices are explained exactly within 2 slides, so you can look at them. And this is the thing I should say. One more thing very still. I mean, let's go to the web page of the course. So as you can see here, you have in the table, you have for the at least starting lectures, you have 2 links in the materials. One link, this is Mathematica file, which you can open only in Mathematica, and you can run it, and you can change it, and you can compute it. And the other file, the second one, this is this CDF file I was talking about, and you can open this file with CDF player. So if you don't have Mathematica, you can install this Wolfram player or CDF player, and then you will be able to look through the material which is provided there. So you simply at home will be able to look once again through this lecture step by step in this CDF format to repeat stuff. So I think that this is, in some sense, after this, my explanation, self-contained, so you will be able to understand and to recall what I was talking about. So please simply do it if you have missed something. Okay, if there are any questions, it's time to ask them. Okay, I can see that there are some remarks on the chat, and that's fact that there are some rules for naming the variables. I wasn't talking about this, but in fact, underscore in Mathematica has a special meaning. I will talk about this later on, and you will learn what does it mean. After underscore, you can specify, among others, you can specify the type of variable. Okay, do you have any questions?
Hello, can you hear me?
Yes.
I have a question. If do we have to do all the exercises from the laboratory or just part of them?
Just try to do all of them, of course, because you have to work hard, but it is not necessary to bring all of them and to have the solutions to all of them. Simply do these which are, let's say, quite easy for you, which you understand and you know how to do them. Of course, if somebody come to the laboratory with no examples and will say that everything is hard for him, so this is not the case I expect here. So hard to specify, I don't know, maybe at least half of the task you should do if you need a number.
Okay. Some of them are quite difficult for me, so that's why I'm asking.
I can understand, of course, and this is why we will meet stationary to explain all this stuff, because normal way of working where there is no pandemic period was that we meet at the laboratory and I'm showing you simple cases. I explain the things you don't understand and then you start working with the examples. So we do something just opposite, that first you work by your own, and then we would do this, and then we will do this at the laboratory. So these exercises are planned just to be opposite, but I'm pretty sure that you, at least part of them, are able to solve them after this, what you have heard during today's lecture. Okay.
Okay.
Any other questions? Yes. Yes. Just to know why it is not possible, or of course, if you would like to, let's say, repair, to change this example, to make it computable, just do it. But in basic, it is enough to know why one cannot compute it. What's wrong? You're welcome. Any other questions? Okay, so if not, it's time to finish. So we will see on Friday with part of you, this who will come to stationary classes. Then we will see or hear during the next week lecture. See you then.
Goodbye. Thank you, sir.
Goodbye, goodbye. Bye.